For Bayesian Statistics. This year we're going to take a little diversion from what I did last year, and for a lot of years. I think this is the year that I go a little bit heavier into MCMC. So I think people want to know how to implement things. It's a good time to know those skills. So if you're an MCMC guru, you can handle any problem. Might take a little bit of time. Might have to be creative in your implementations and pick up those skills. But you can kind of handle any problem, any Bayesian problem, and probably any inference problem or forecasting problem. And the only thing you give up is time. Of course, the name of the game in algorithm building is speeding your algos up. And so we'll be talking about that. But you can kind of do a pretty clumsy implementation and usually get through a problem. If you need to repeat everything, you might want to get more sophisticated and work on developing a better algorithm. I'm going to be telling you about theory, implementation, and how it all applies to Bayesian analyses as we go. I need to tell you a little bit about Markov chains at large before we can understand what we're doing. So what I'm going to do is I'm going to kind of illustrate where we're going. I'll run a little demo for you. Then I'll tell you some terminology that we'll be using, a little bit of Markov theory that will extend as we go. And some problems that we can apply MCMC to in the homework. So I kind of have to rewrite some of my homeworks too for you guys. So I'll probably be doing that tomorrow and have a homework prepared for you on Wednesday. Okay. Before we begin, somebody asked me a question about a homework problem that has to do with MLEs versus MAPs. So maximum likelihood estimators versus maximum a posteriori estimators. These are maximum likelihood estimators versus max a posteriori estimators. So basically, you look for the argument that maximizes that thing that's your estimator. So anybody that's been doing classical steps for a while is certainly looking at MLEs. Bayesians like to do a little bit more to the likelihood. They like to multiply by a prior, and then they might maximize that thing. So there's a lot of different types of estimators out there. There's means, there's medians, there's modes. Those are kind of the famous ones, and then there's other stuff, weighted averages. So those are kind of my favorite, and everything can kind of be framed in terms of that. It just depends on what their weighting functions are. MLEs have an interesting property. So let's say I maximize some posterior distribution. I'm going to stick with our typical notation. Max likelihood theta given x. And you might want the argument that maximizes everything over theta, and I'm going to call this theta cap MLE. So picture, my likelihood looks like this, and the MLE is this thing. It's the maximizer of that function. MLEs have a nice property that, let's say you're talking with somebody and you say, I did this exhausting work, I wrote down the likelihood function, and I maximized it. That can be an arduous task. It sounds like a very trivial thing, but in hiding space, sparse spaces, multimodal spaces, it's not an easy problem. So optimizers, people that do optimization for a living, they study this problem. And people that are very good at it study a slice of the problem. That in a particular space, they know the optimal algorithms. So academics do that. Over in ISE, they make professions out of this. We have an application of it. Maps, I drew you a picture last time. Instead of writing the likelihood down, have a posterior here and you maximize it. Likelihoods have a nice property. So if you say I did all this arduous work and I got this for you, and somebody says, oh, shucks, I don't ever like to talk about theta. I like to talk about some other parameter, which is a function of theta. You can say, okay, no problem. Here's what we're going to do. I'm going to take my MLE, plug it into this function, and that gives you back the MLE for the parameterization you were talking about. So it turns out MLEs have that property. You can always do this, no matter what. So it doesn't matter if F is invertible or not invertible. So it doesn't need to be. This still works. Just take your MLE, plug it into that. So if you're talking about something like variance versus precision, if you have the MLE for variance and somebody says, I want to talk about precision, just give them a reciprocal, and it works. So you don't have to go through a new maximization problem. So the invariance that we're talking about is with respect to the transformation. Anytime you see this word, invariance, ask all about it. What is not varying? What do you mean? Because in any system, some type of problem they're talking about invariance is with something specific related to that problem. They change something, but everything just moves through smoothly. So in our case, it means this. So that's invariance of the transformation of MLEs. So we usually say MLEs are transform invariant. It means I can just transform the MLE and give you the new MLE for the new parameterization. Maps don't have this property in general. And so, in general, it is not true that I'll say theta hat map, whatever this function is, it's not usually true. This thing. Let me say this a little bit easier for you. It is true that they're usually not equal. So, now, it depends on which type of problem you're working on. It depends on the transform that you're talking about. It turns out there's a special class of transforms where this property does hold for Bayesian analysis. The reason I throw this out is I saw somebody giving a talk a long time ago, and they did this. It's like, it's not true, and it's not true for your problem. So that estimator you just brought in, we need to look at something else and see how close this analysis is to being accurate, so that we can at least save your talk for the purposes of the audience. I think it made a dramatic difference in the talk that I saw where somebody applied this. And they told me that they thought they were thinking about MLEs when they did it. It's not true. It's not true. So, something very different between likelihoods and posterior distributions, or just distributions in general. Likelihoods and distributions are different things. A likelihood is not a distribution. A likelihood function. What's the difference?
Range of blends of things.
Yeah, the randomness of it. So that it's a random measure. So Mohammed's jumping ahead in answering a full-blown question. But yeah, essentially a posterior is off from a likelihood from the prior. But there's also a mathematical thing we have to distinguish. One of them is an actual random measure. And so the thing you need to consider when you're dealing with a posterior or transforming a random measure is that Jacobian term. So for likelihoods, when you transform them, no Jacobian comes in. You just do the thing inside the function. So invert that thing, map it back, stick it in the likelihood function. For posterior, you also need to multiply by the derivative. So in 1D, it's the derivative. I'll let you think about that. I can give you a counterexample right now against it. Imagine your posterior is normal 0, 1. Just make this real easy. I did a data calculation. I computed everything, I figured out my posterior was normal, and just by chance, guided by the data, the mean is 0 and the variance is 1. Probably never happened for you. The probability 0 that happens, but in my hypothetical universe, just happened. If I look at the random variable, so the posterior measures 0, 1, so let's call that theta. So theta is distributed, normal 0, 1. If I were interested in the random variable theta squared, what distribution would it fall? Chi-squared, with 1 degree of freedom. So do you know what the map of the normal 0, 1 is? It's 0. Do you know what the map of the chi-squared with 1 degree of freedom is? Yeah, it has something to do with degrees of freedom, but it's definitely not 0 because it's pulled away from 0. It's a positive measure. And so whatever it is, it's not 0. So you can't just take 0 and square it and figure out what the new thing is. You need that Jacobian term coming in over there, and that's the thing that's sliding everything over. So think about that a little bit. I've given you the answer to the problem, but I want you to think about it more deeply. Which class of problems have invariant maps according to this version of invariance? So that's at least what I'll say about it right now. In Casella and Berger, or any inference book, so that's kind of the brand name choice that most graduate schools use these days, the proof of this statement is one line if this is an invertible function. If it's not invertible, I just have to redefine for you what I mean by the inverse. And then it's 2 lines. So it's actually a pretty simple proof. I would encourage you to look at it. It's a proof of that statement that I wrote in the homework problem. Think about the derivative, how it comes into play right here. Think about in which cases are derivatives constant. Then really everything's just likelihood.
Do we really need the derivative constant, or do we just need it to be non-prime?
You need the derivative, yeah. It's probably something different from what you're thinking right now. Oh, do you really need the one-to-one thing?
No, I could
Okay.
I'm just like, okay.
If it's monotonic functions in general, think about my squared example. That's monotone in the positive part.
It's a minus square.
I see. So you're going from that, yeah. So slightly, it's actually much more strict than that. The class is monotone, so good insight. But it's a much narrower class than that. So keep thinking about it. Jingman, you got something? You look excited. You got the answer.
I'm just thinking about just that Jacobian term is a function of the inverse function and prove that it's not equal.
That's right. And in some cases, you might have some equality. So you figure out in which cases you do have equality. So good insight. Anyway, something to think about. I'm going to come back around and I'll make sure you know the answer to this question by the end of this class. What did I just say? What's that?
That thing equals to multiple subsets.
That's not what I just said. Sierra, what did I just say?
It's on a test.
It's on the test. You're welcome. MCMC. Markov chain Monte Carlo. We've got a lot to discuss. This is probably the biggest tool in the Bayesian handbasket. This is probably what made Bayesians popular. That you could actually solve their problems instead of just talk about how good the solution would be if you could do it. So the 60s looked like that. 70s looked a bit like that. 80s started changing. You know, maybe a little bit earlier, maybe the 70s or the 60s if you worked in a really high-powered university and you had a gigantic supercomputer that's weaker than your watch nowadays, could do problems. But it took until the 90s for this to really catch on. The reason why is computers. I'll give you a nice introductory talk that I sometimes give at universities on MCMC, but I want us to get through some of this so you can understand it. So what's going on there? I'll show you some of my contributions to the field as well. I like playing in this field. Every couple of years go by, I have to write a new MCMC paper. It's always kind of fun to come back around and do it. I get some problem where I'm like, ooh, I came up with a better algorithm. For this, it works really nicely. And then I try to generalize those principles and I'm writing a more mathematical version of it. So, you know, it's some fun stuff to play around with if you're into computation. This is probably what lured me into statistics in the first place, is the algorithms. I knew I could be useful. Then I started getting into Bayesian statistics. I was like, wow, the properties are so cool too. Can you prove it? And so whatever got you here, this is cool. The theory's also cool. The nice thing about all this theory is it extends to almost everything in statistics as well. And so in Monte Carlo samples, we want to reduce variability. Don't want a lot of variance coming in from Monte Carlo variance that we have to average out. So that's like what statisticians do. In the world of designing experiments, that's exactly what they do. Okay. Let me show you a couple things first. I'll try to convey to you, this is important. So real quick, as I set this up, somebody look up for me the top 10 algorithms of the 20th century. Just like all things, if you have two good things, somebody needs to know which one's better. So it's human nature. So we live in a multi-dimensional universe. Maybe nothing's better than anything else. It's just in certain aspects. So I think in terms of utility, the algorithms that we're about to study have been recognized. Olga, I see you over there on your phone. So what have you got?
Like all of them? All top 10?
Why don't you read number one?
Number one is the Metropolis stuff.
Metropolis. So number two?
Simplex.
It's my second favorite algorithm as well. So I might have been skewed once upon a time, but I used to like simplex a lot. What's number three, just for the fun of it?
Carlo subspace method.
Krylov, subspace methods,
Oh, okay.
regression techniques. So I hear stats when I hear that. I hear regression, but other people think about it differently. Not sure that's what everybody was thinking about. And they wrote it down. It was kind of finicky when it changed the inputs. Let's have a look at what Olga was looking at. So while I asked Olga to check her phone right before class, I didn't tell her which website to go to. This is pretty easy to find online. This is from class over at Cornell. This, I think, is the first kit I came up with on my Google query. Yours might be a little bit different, depending on what you search. So, but I think this is the same list. Usually you come back to a list that's very similar to this. The IEEE at the turn of the century, this is now 20 years ago, did a survey on this, and they tried to distinguish the most popular algorithms. So some of these things, it's almost funny when you see it, but when you study this stuff, you'll go, it's revolutionary. It really did revolutionize something. So it's like the Fortran compiler. It's still the fastest thing on the block. So can't be beat yet. Still quicker, produces faster code that's written properly. So people doing fluid simulations like that, because they need to run it quick. Differential equation, you guys will still see using this stuff. It's still faster. Simplex, I kind of like it. It's an optimization scheme. It's really a Lagrange multiplier technique. So it's an algorithm for finding solutions to linearly constrained problems. So very interesting. So I like that algorithm because it doesn't just tell you the solution to the problem, but it also tells you Lagrange multipliers, which tell you if you let up a constraint, how much would you get back? So if you change something in the problem, how much would it increase your optimum? I love that. It doesn't just tell you the solution, it tells you other things about perturbing the system. So I think I like that because I'm a statistician, even though this isn't a statistical thing. When I took it, I just found this online before I came in. They're talking about a new course, Top 10 Algorithms of the Century, MAP 224 CS339 at Stanford. I took this class. So I thought it was pretty cool. I didn't really understand Metropolis as well as I do now, but what I did understand at the time is I could implement it really easy. So at least some of the more basic pieces of it. And I think that's where some of the popularity comes from. But what's Metropolis used for? Well, it's a general purpose sampling algorithm to be used for anything. Bayesians use it. Why? Because we know likelihood times prior, we'd like to be able to sample from it. Because we can't do the math. So if we could sample from it, then we could learn any answer we wanted. If we wanted means of the distribution, we sample from it and take the arithmetic average. Just crank up the number of samples really high. You have control of that. All you have to do is wait. You wanted variance or intervals or something like that, you could sample from the distribution and estimate them. In the homework problem 2 today, I had to sample 10,000 iterations from each beta to estimate the quantile of the distribution. If you didn't know there's a quantile function on your computer, mine's in my top left-hand corner. I just push it, it gives me the quantiles of it. It's built into R, it's built into MATLAB. So you wouldn't have had to do MC to estimate those boundaries, the 0.025 and the 0.975 tail probabilities, those critical thresholds, those quantiles. So the faster way to write that code would be to invoke the quantile function, but I asked you to estimate it using MC. So you can kind of learn this thing that you can do it. It's not necessarily what you always want to do, but in terms of getting an answer, as long as you can wait, no big deal. In the implementation I gave you for the homework, everything was independent draws. It was not Markov chain Monte Carlo. It's just plain Jane vanilla Monte Carlo. It's sample from the distribution, piece of cake. Every sample I got was correct. How was that implemented on your computer? We need to talk about Monte Carlo. So what they're actually doing, how they're estimating all this stuff. Anyway, the key point here is Metropolis is at the top of the list. And this list is written by engineers, not by me. So, does anybody know who Metropolis was? Nobody? So, physicist working at Los Alamos. He wants to understand things about electron layouts. He's got big computers around him. So, figures out how to use them and how to turn this into a probability problem. They already thought about these probability problems, Boltzmann distributions. So he wanted to sample from them. There's some other players that come in, but Metropolis was doing this back in the 50s. And so he's an early purveyor. He has an interesting problem that he wants to work on. Does anybody know what the problem was that he was really working on? Nuclear physics. So, you know what he was doing? Well, trying to save the world. Oops. So, working with all of them. So, anyway, the method persists. It's been extended, and it's gotten kind of this generalized name that we'll talk about. There's another player, Hastings, that came in, and that's the variant of the algorithm that I'm going to talk about today. But usually when people walk around and they say Metropolis, they're talking about the Metropolis-Hastings algorithm in general. Hastings came in 3 years later and introduced a new idea in another paper. I'll talk about the distinguishing parts of those papers as we go. Let me show you a quick demo. So, I want you to think about this problem that we've talked about before. So my demo corresponds to this thing. That distribution, and we've talked about that distribution before. So this is the normal example where I've parameterized everything in terms of precision and the mean. And I've used reference primers for my analysis. So my posterior is proportional to this thing. And we've thought about that function before. I told you it was triangular. It's kind of hard to see. What distribution is that? So Mohammed says it's a gamma.
Poisson?
It's not Poisson because nothing's a count. So Poisson's count things. U is continuous, P is continuous. So Mohammed's gets half credit because in phi it looks gamma. There isn't E in the Poisson thing. So this is the name of the game in this class. Let's get our distributions. But we've got time. In terms of mu, it kind of looks normal. It's e to the minus something. But there's a relationship between phi and mu. And that's where we're struggling. We don't know how to characterize it. I don't know what this distribution is. It has this bivariate relationship that I'm unfamiliar with, and I wouldn't know what to call this. I don't know what to call it either. I think they call it normal gamma. So just for lack of creativity. So what does it look like? We don't know. How do I sample from it? There's no button in my top corner. So this button right here I've replaced with my quantile function. Push it, it's a joke. But I don't have a button on there for mu phi sampling. And there's no built-in function on your computer. You got something?
We're assuming that both CR is a T distribution.
If I integrate out mu, it looks, or if I integrate out phi, it looks T. So there's your connection. So the margin of mu in this distribution is T. Conditional on phi, it's normal. Phi conditional on mu is a gamma. Phi with mu integrated out is a different gamma distribution. And the bivariate relationship is right there, and we don't know what to call it. So all of the things except for the joint distribution we probably understand and are familiar with, but we don't know this right here. I think this is an extremely important problem. Especially in cases where you don't have a ton of data. Everybody likes to talk about the big data case. I still work with people that are like, I've got 40 data points. You know, and a lot of different things. It took a lot of time to get that. I would agree that this wears off as you get more and more data. But if you are in the situation where you don't have a lot of data, characterizing the joint relationship between these two variables is probably very important. Especially if your decisions, you know, being better by 1% makes a big difference. A lot of problems are just like that. So medicine, finance, anything that you do, 1% is better. So better is better. We'll stick with that principle. I wrote a piece of code to do this sampling. I'm going to show you this code soon.
Flip your screen.
Thank you. Okay, so I'll be walking you through it. You're going to be writing versions of your code yourself. Turns out this problem is a bit too simple for us. Turns out a Gibbs sampler would knock this problem out of the park. And it would converge so fast to the right thing that I wouldn't be able to convey certain messages to you. So I've done something, I've anti-tuned my algorithm to slow it down so we can look what good tuning is. When you get this problem on the homework, it's going to converge way faster for you. Okay? So there's a lot of learning lessons built into this code. Things I would not do in practice, but they help us to convey our points. Let me just show you. This is pretty well tuned already. I've generated some data from my original problem. I'll just generate some new data. So that's new data that I got. There's true sigma and there's true mu floating around. I needed to know those parameters before I could generate my problem, before I could infer everything. So I need the data to be generated under the truth. Now I'm going to go back and try to figure out what the truth was. So I know what true sigma is in true mu because this is a simulation study, but usually you don't get to see these. True mu is 100 in my case, and true sigma is 2. So I just made up some numbers so we can eyeball my graph. I'm going to use these numbers in my code that I've developed, but I'm only going to use them to compare back the answers that I get. I'm only going to use them in a plot. You're going to see where the truth is in the plot, and then I'm going to use the data to do the rest. So the only place the truth gets used in my code is for reference. It doesn't get used in my algorithm. Let me point out to you, the biggest mistake you can do in my class is to use the truth in your inferred answers. If you knew the truth, you wouldn't be doing anything. So I get back mu and phi, so I've reparameterized everything. I've brought it in on the sigma scale, and I give it to you on phi scale. So I give it to you on 1/sigma squared scale. Why? Because I like working with gamma distributions. Saying that, my code doesn't know anything about gamma distributions. It's going to pretend it doesn't understand anything about these distributions. All I have is that formula. So product of phi to the 1/2 exponential terms, the sums of squares appear, and then the reference prior phi inverse. So I've got that formula and that's it. And that's all I use in this code. In your code, you're going to actually use things like normality and gamma. You're going to know about them. But what's cool about this algorithm, the way that I've implemented it, is even if I was totally naive about every result out there, this will still work. And that's the beauty. That's what's nice about it. I don't need to know anything theoretical. I run everything. That red dot in the middle of the screen is the truth. That's the only place I use it. So if you look at it, mu is 100, and phi is 1/4. 1/2 squared. So sigma was 2. 2 squared is 4. Inverse of that is 1/4. So there's my truth. I've got new data. My data vector is 10 data points long. These are my samples. So I'm plotting the samples for you. I'm drawing a line between the samples. Every 1,000 or so iteration, I show you the previous 1,000 iterations, and then I'm just highlighting where everything else was. Those are all my samples at the end of the day, from mu and phi. So let me just ask a quick question. Why is this thing not centered in the truth? You can kind of see what the truth is. Let's look at some of these plots. Stare at some stuff real quick so we can understand my output. The truth is right there. Why is that not right here in the middle? Is that what you would have expected? We have 10 data points. So hopefully the black stuff overlaps the truth. So it's because it's a simulation. It's never going to be right in there. If I get an infinite amount of data, it will start being right in the middle, and my posterior would collapse to a point mass of mine. So I got more and more data. So that's how simulation results work. Every once in a while, my red point should probably be like way over here. So we could do it again. Let's just do it one more time. I'll show you the other graphs in a second. But this is what MCMC does, is it gives you a bunch of samples back, and they're connected. They're moving slowly through the space. So one more time. The lines are showing you where the last draw was. So it shows you how much it moves. In 2 dimensions, we call that a trace plot. Nobody ever likes to look at trace plots in 2D. They look like hairballs. So, same exact thing, because my data is the same. I have slightly different realizations here, but it basically looks the same. Let's get new data. Boom, same truth, new data. Run MCMC. Modern Bayesians sit there and stare at this thing as it evolves. Staring at trace plots. Pretty fun. Kind of cool. Just kind of moving around that space. It's exploring, seeing stuff. Here are my samples at the end of the day. Kind of went out here for a little while. I bet there's another little chunk out here that just didn't explore yet. We know this thing should be symmetric. So it hasn't run long enough. So if I ran it longer, it'd probably pull that out a little bit. That's the name of the game. So 2 samples don't do it. 100 samples doesn't do it, but a bazillion will do it. So the idea is, as I sample longer and longer from this distribution, I converge to samples from my actual posterior. So it's an eventually sort of thing. This is an iterative algorithm. You can kind of see that flow through. I've plotted the margins of the distribution. The joint's kind of hard to look at. So I've plotted 2 sets of margins, both for phi and for mu. So let me just ask you a question. So I've just plotted up over the iterations. We can see it's kind of this fuzzy thing. So when I say the algorithm converges, it converges to a distribution. Those histograms is what it's converging to. So my samples are always coming from the right distribution. So in math class, when they say converge, they mean to a point. When I say converge, I mean distribution. And then there's some stronger terms. How does it converge to that distribution? In my case, almost surely. We're not going to talk about that in this class, but in the strongest sense, it converges. What that means is that when I finally start sampling from the right distribution, I don't leave it. So it's not that the probability of leaving it is kind of decreasing. It means once I'm there, I stay there except on an unmeasurable set. So don't expect to see that on a computer. So what we get out of computers is measurable stuff. It's all finite. So let me ask a question. What distribution is that? Say it again?
Normal, mean, mu, and precision variance like the field right now.
Yeah, but maybe like mean X bar or something. We only have 10 data points. So you can run it for a long time. That doesn't mean it's converging to mu. It's still converging probably to X bar. Does anybody else want to gander a guess what distribution is that? Well, I'm usually right, so normal? It's not. Let's look at it. So I've got a mu vector. So I got all this stuff right here. So I've got mu and phi vectors. Let's look at mu. It's a big, long thing. I asked for a ton of samples. This is what MCMC gives you back. So the output of MCMC is like a gig file that you get. So we'll talk about all that. So you're at the mercy of storage. Back in the day, this was a big deal. But I could end up looking to see if this is normal. QQ plot. Mu. Boom. Let's look at a new figure. Figure 3. Oops. Wonder which one I just overwrote. No, I overwrote that one. Let's rerun the whole thing real quick. I need all my figures into this. Doesn't take too long. That's MCMC. Looks good. You're gonna see, you see it start doing that kind of stuff. You're like, whoo, waited 3 weeks for this to fucking work. Finally found my error. So, there are my plots. Let's look at another plot right here. Figure 4. Mohammed says it's normal. I think this is a worthwhile lesson. Figure 5, new figure. QQ plot. Does anybody know what a QQ plot does? So I sometimes ask people to use them. I'll ask people to use them next time. If you don't specify the distribution, it'll always compare against the normal 0, 1, which is equivalent to comparing against the normal mu sigma something. What it does is it looks at the quantiles of the normal distribution, so those are the theoretical quantiles, and it looks at the empirical quantiles from the histogram that you build from your samples, and it compares them to each other. You can compare any 2 distributions to each other this way. By default, people usually compare to normal, so I didn't have to specify anything. I can compare empirical quantiles to empirical quantiles. If they have the same location, and if they're part of a location scale family, and it belongs to the same family, that thing is going to be a straight line where the location and scale just control where that line is. But straight line tells you they're the same things. So I drew a straight line there so that our eyes, no matter how bad they are, can tell that blue thing is not a normal distribution. So I knew theoretically something about this. That you know it too. What distribution do you think this is? So what does this say right here? It's saying that the tails right here, so the right tail, longer quantiles, bigger, heavier tails than normal. And these have heavier tails on the other side. It's a T. Which T?
1 with 9.5, I guess.
So it's a T9. And so I could verify that. And so what I got out of my code were the joint samples, mu and phi. So they're sampled together. When I just looked at one column, I got the margin. It's marginalizing force for free. So that's what I keep saying on the computer. When you do this, you're marginalizing for free. So you have joint stuff, and you have the margins. Isn't that awesome? In a high-key problem, it did all your integrations for you. So what is this histogram? For feet. It's a gamma. Which gamma is it? This was your homework problem, right? So key phi given x where you have to integrate out mu. So that's one of your homework problems, and there's a little square root 2 pi b term. If you forget it, you mess up the problem. So it's some gamma. So it has some n-1s and not n's. So it has everything to do with the n-1s and not n's in that case. So good problem for review session. I didn't need to know it, I just got it. I could check the QQs for that to verify. And I've got my joint samples as well. So I have everything about their association. That's why we like MCMC and sampling, because it does a bunch of math for you. It does calculus for you. It's integrating over things. So that's the whole idea. How would I get conditional samples? If I wanted to know what this thing was where mu was just fixed at 98. I wanted the distribution of phi where mu was 98. Turns out it's these samples right again. If I wanted to know where the samples were for mu given when phi was 0.8, they're these. Right there. You wouldn't actually sample them that way. You would fix phi at 0.8 in your code and never update it. And then you would get conditional samples. So you can get conditionals. The code would run fast if you're not updating phi. You get the joints and you get all the margins. So if you can sample from a problem, you can solve anything. Very nice. If I wanted the posterior predictive, then I would pull these samples out and I would plug them into my sampling distribution and sample from my sampling distribution. So if I wanted to forecast, and I didn't know that that distribution was a t with n minus 1 degrees of freedom, had something to do with s squared over n, x bar. If I didn't know that, I could use these samples, sample them into my normal distribution, and pop out a sample from the normal distribution. I've got predictive samples. Sweet. I think because we've spent so much time just kind of getting acquainted with what this column is and what we'll get at the end of the day, I want to just point to this shape right here. What does it all mean? I guess it makes sense to me after I stare at it for a while, but it says if B is very small, that means there's a lot of variance in the problem, and I'm more uncertain about B. But if B is big, then I'm very certain about what mu is because the variance is smaller. That's what that relationship is showing us. If I want to forecast, I should integrate over that space. And that's what that two-step sampler does that we talk about when we talk about predictive distributions. I think next time when we come in, we are going to start getting acquainted with what Markov chains do. If you want to have a look ahead, I want you to look up a few terms. What a Markov process is. In a temporal process, it means that the process is only dependent on the previous time step. I'll write that down a little bit more formally next time. Markov chains, think about what they are. They're these matrices where the rows sum to 1. They all have positive elements. So the probability distributions on transitions. I'll walk you through that. I'll show you what Markov chain Monte Carlo does. I'll describe it in words. I'll tell you what a limiting distribution and a stationary distribution is. If you get as far as being able to distinguish this, I'll give you some extra credit points. Just tell me before class that you know the difference between a limiting and a stationary distribution. So see if you can figure that out. And then I'll tell you what the Metropolis Hastings algorithm is, what I actually just deployed. What I actually did is I did Metropolis within a give sampler to really slow it down. Sometimes that's a good move, but I designed my move to move slowly so you can see everything that was happening. We'll slow down those steps. We haven't discussed the eventually term. It looked like in my code, all my samples were good. And that's because I cheated. I started in the stationary region of the distribution. I knew where it was, I started it near the truth. So usually you don't know that part. So we're going to come back, I'm going to slow down my algorithm even further, we're going to run through these terms, and at least get to this. Then I'm going to show you how you prove this thing works in a nutshell. So we'll go through a little bit of proof, and then we'll go through some implementation details, the part that spends everybody's grad program. Got some error in my code. So all I want to do is sample from this distribution. I can't find my mistake. So I'll give you some pointers on how to look for your mistakes and some stuff that hopefully you don't waste a week on. Let you waste a week on some other more technical thing. That's it for now, Jeff. Thanks so much.